For decades, the cockpit of early high-performance aircraft was celebrated as a triumph of modern engineering. It was the place where human perception finally caught up with aerodynamic ambition. Designers spoke of visibility as liberation. The pilot would no longer peer through thick frames and narrow slits. Instead, the sky would open in every direction, unobstructed, clean, absolute. The cockpit canopy became a symbol of progress, a transparent crown placed atop a machine that promised to dominate distance, altitude, and time. The architecture of confidence began with materials that, at the time, were considered revolutionary. Acrylics and early polycarbonates replaced heavy glass. Aluminum alloys formed slender frames that hugged the canopy with minimal intrusion. Rivets were countersunk, edges smooth, transitions sharpened into elegant curves. In wind tunnels, the airflow remained attached. In static load tests, the structures held. On paper, the cockpit was strong enough. In practice, it appeared flawless. Certification reinforced that belief. Engineers loaded the canopy beyond expected pressures. They exposed it to temperature gradients, vibration profiles, and simulated bird strikes. Each test ended the same way. No catastrophic failure, no visible cracks, no reason to doubt the design. The cockpit was declared safe, robust, and ready for service. The aircraft entered the world carrying not just passengers or weapons, but confidence bordering on certainty. What no one could see was that visibility came at a hidden structural cost. Transparency demanded thinness. Thinness demanded tight tolerances. Tight tolerances created unforgiving stress geometries. At the interface between metal and transparent skin, forces concentrated sharply. Aluminum expanded and contracted at one rate. Acrylic responded at another. Each flight cycle imposed differential strain that never fully disappeared when the aircraft returned to the ground. On the drawing board, these effects were averaged, simplified, assumed elastic. Engineers believed the materials would return to their original state after every climb and descent. They trusted the mathematics of ideal behavior. What they underestimated was the cumulative nature of fatigue. Not the dramatic failure that appears in textbooks, but the microscopic degradation that hides beneath smooth surfaces and polished clarity. With every pressurization cycle, the cockpit shell flexed outward, then relaxed. At altitude, internal pressure pushed relentlessly against the canopy. On descent, that force reversed. Temperature swings compounded the effect. Sun-heated ground operations followed by sub-zero cruise altitudes created thermal shock that propagated through dissimilar materials. At fastener holes and canopy edges, stress intensified beyond what early models predicted. Inside the metal and plastic, cracks were born. They were invisible, sub-millimeter fissures forming along molecular boundaries weakened by repeated strain. These cracks did not threaten the aircraft immediately. They grew slowly, incrementally, obeying fracture mechanics with mechanical indifference. Each flight extended them by microns. Each landing disguised the damage beneath intact transparency. The process was silent. Pilots saw no warning lights. Maintenance crews found no obvious defects. Visual inspections revealed smooth surfaces and acceptable tolerances. The aircraft continued to fly, accumulating hours and cycles, carrying its invisible wounds forward through time. The cockpit, still clear to the naked eye, began to betray subtle signs. Light refracted oddly at certain angles. Glare intensified during low sun conditions. Distortions appeared at the edges of the pilot's field of view. These reports were dismissed as nuisances. Optical artifacts, human perception errors, environmental effects. No one suspected structural degradation. The canopy had passed its tests. The design was certified. Confidence remained intact, even as the material quietly weakened. Crack propagation followed a predictable but unforgiving path. Once initiated, cracks sought regions of higher stress. They branched outward from rivet holes and frame transitions. Vibrations from engines amplified the process, introducing high-frequency loads that accelerated growth. Over time, the crack length approached a critical threshold. Beyond that point, failure was no longer gradual. It was inevitable. The catastrophic sequence unfolded without warning. At cruising altitude, with maximum pressure differential across the cockpit shell, the structure reached its breaking point. A crack that had taken thousands of cycles to grow reached critical length in an instant. stored elastic energy released violently. The canopy failed not as a slow leak, but as an explosive rupture. Decompression was immediate. Air rushed outward at extreme velocity, tearing fragments of the canopy free. The pressure wave struck the pilot with brutal force. Wind blast filled the cockpit, ripping loose unsecured equipment, shattering instruments, and overwhelming human strength. In some cases, the pilot was incapacitated instantly. In others, control was lost as aerodynamic loads shifted unpredictably around the breached structure. The aircraft itself responded with mechanical indifference. Sudden loss of cockpit integrity altered pressure distributions along the fuselage. Structural members designed for symmetric loads experienced asymmetric stress. Secondary failures followed. Control surfaces fluttered. The aircraft entered unrecoverable attitudes. In accidents where the airframe survived long enough to land, the damage revealed a truth no one wanted to accept. The cockpit had been the weakest link. The immediate aftermath was severe. Fleets were grounded. Manufacturers issued urgent bulletins. Airlines and military operators demanded answers. Aircraft that had flown safely for years were suddenly suspect. Investigators approached the problem with forensic precision. They removed canopies, sectioned frames, and examined fracture surfaces under microscopes. What they found dismantled decades of assumptions. Fracture surfaces revealed classic fatigue striations. Crack origins traced directly to stress concentration points at window corners and fastener interfaces. Thermal expansion mismatches were measurable, repeatable, undeniable. The failure was not random. It was engineered, slowly and invisibly, into the design. The root cause was not a defective batch of material or a single manufacturing error. It was a systemic oversight. Cockpit structures had been excluded from comprehensive fatigue life analysis. Visibility had been treated as an ergonomic feature, not a structural one. Certification standards had not required full-scale cyclic testing of transparent components under realistic thermal and pressure environments. The investigation forced a reckoning. Engineering arrogance, born from early success, had blinded designers to subtle physics. The belief that transparency equaled simplicity proved false. The cockpit was not just a window. It was a pressure vessel, a load-bearing structure, a critical interface between human and machine. From failure emerged reform. Window geometries were redesigned with generous radii to reduce stress concentration. Multi-layer laminates replaced single-layer acrylics. Materials were selected not just for clarity, but for matched thermal expansion coefficients. Redundant structural paths ensured that no single crack could trigger catastrophic failure. Fatigue testing protocols expanded to include full-life pressurization cycles for cockpit components. Modern canopies became thicker, heavier, and more complex. To the untrained eye, they looked overbuilt. To engineers, they were a confession. Each layer, each curvature, each redundant fastener represented a lesson paid for in damaged aircraft and lost confidence. Visibility was preserved, but never again at the expense of structural integrity. Today, every cockpit carries that legacy. Pilots look through canopies shaped by past failures, protected by materials engineered to resist not just impact, but time. The clarity they experience is no longer fragile. It is earned. It is reinforced by fracture mechanics, fatigue analysis, and an understanding that physics does not negotiate. The history of aviation is written with steel, ingenuity, and the will to challenge limits. It is also written with cracks too small to see, growing patiently until arrogance gives way to reality. Welcome to the vault. Confidence, once established, is difficult to dismantle. After the first failures, the industry did not immediately accept that the cockpit itself was the problem. Engineers searched elsewhere. They questioned pilot behavior, maintenance procedures, operational envelopes. The aircraft had flown for years, thousands of hours, tens of thousands of pressurization cycles. If the cockpit were fundamentally flawed, it should have failed earlier. That assumption delayed the truth. The second phase of understanding began not in the air, but under laboratory lighting. Investigators returned damaged canopies to materials labs and began to treat them not as components, but as crime scenes. Fracture surfaces were cleaned, etched, and examined under scanning electron microscopes. What appeared smooth to the naked eye revealed a complex landscape of striations, arrest lines, and branching cracks. Each mark represented a single load cycle. Each line was a timestamp written by physics. The geometry told a consistent story. Cracks almost always initiated at sharp corners where transparent panels met metallic frames. The design language of early cockpits favored angular transitions. Straight lines were easier to manufacture, easier to seal, easier to align. What engineers failed to fully account for was how stress behaves at discontinuities. In those corners, stress was not evenly distributed. It multiplied. Stress concentration factors exceeded safe margins during normal operation. At altitude, internal pressure forced the canopy outward, bending it against rigid frames. The highest tensile stresses appeared precisely where acrylic met aluminum. Thermal effects compounded the problem. Aluminum expanded more than acrylic under heat, then contracted more rapidly in cold. That differential movement sheared the bond lines, loading fasteners in ways never intended. At the time of original design, computational tools were limited. Finite element analysis existed, but models were simplified, constrained by processing power and incomplete material data. Acrylic was treated as isotropic, elastic, predictable. In reality, it was none of those things. It exhibited creep. It aged under ultraviolet exposure. Its fracture toughness degraded with time. None of these factors were fully modeled. The error was not ignorance. It was assumption. Engineers assumed that materials behaved ideally because they had no evidence to suggest otherwise. Early testing reinforced that belief. Static tests passed. Short-duration fatigue tests showed acceptable results. What was missing was duration. No one tested what happened after 10,000 cycles, or 20,000, or 50,000. The cockpit was certified for strength, not for life. As aircraft fleets aged, the invisible degradation accelerated. Crack growth followed Paris law with brutal consistency. Growth rate increased exponentially as cracks lengthened. What had taken years to initiate now required only months to become critical. Aircraft that survived early service entered a danger zone where failure probability rose sharply. Maintenance schedules, designed around visible wear, offered no protection against microscopic fracture. Some pilots reported increasing difficulty seeing clearly during certain phases of flight. Sun glare intensified unpredictably. Reflections doubled. The canopies seemed to warp light. These were not optical issues alone. They were structural. Microcracks altered refractive indices, scattering light in subtle but meaningful ways. The cockpit was no longer optically neutral. It was signaling distress. Still, no alarms sounded. The aircraft flew on. When the next catastrophic failure occurred, investigators were ready. High-speed pressure data, structural telemetry, and cockpit voice recordings painted a precise timeline. The failure initiated at a known stress hotspot. Within milliseconds, crack propagation accelerated beyond control. The canopy fragmented. Pressure equalization occurred faster than human reaction time. The event was not survivable. This time, the industry listened. Regulatory agencies demanded comprehensive fatigue life reassessment of cockpit structures. Manufacturers were forced to confront uncomfortable truths. Designs once praised for elegance were now liabilities. Aircraft that had defined an era were grounded pending modification. Confidence gave way to caution. The forensic phase expanded beyond individual aircraft. Investigators reviewed decades of design philosophy. Why had cockpit visibility been prioritized so aggressively? The answer lay in competition. Aircraft manufacturers raced to offer pilots superior situational awareness. Wider fields of view promised tactical advantage, safety, and market appeal. Each new model shaved away structural framing, pushing materials closer to their limits. Success reinforced the approach. No one wanted to be the first to add weight back in. That decision carried a hidden price. By reducing framing, designers transferred load-bearing responsibility to the canopy itself. Transparency became structural. Acrylic, never intended to act as a primary load path, was forced into that role. The cockpit was no longer a reinforced opening in the fuselage. It was a stressed shell. Once this reality was acknowledged, solutions followed, but not easily. Redesigning cockpit structures meant revisiting fundamental assumptions about aircraft layout. Window shapes changed first. Sharp corners disappeared. replaced by generous radii that distributed stress more evenly. This single geometric change dramatically reduced crack initiation rates. Material science followed. Single-layer acrylic panels were replaced with multi-layer laminates combining different polymers, each chosen for specific properties. One layer provided optical clarity. Another absorbed impact energy. A third arrested crack propagation. Bonding techniques improved. Adhesives replaced mechanical fasteners where possible, eliminating stress risers. Thermal compatibility became a design requirement. Materials were selected based on matched coefficients of thermal expansion. Where mismatches were unavoidable, flexible interfaces were introduced to absorb movement. The cockpit was treated as a dynamic system, not a static enclosure. Testing protocols evolved dramatically. Full-scale cockpit sections were subjected to accelerated life testing. Pressurization cycles simulated decades of service. Thermal chambers reproduced extreme temperature swings. Vibration rigs applied realistic engine-induced loads. Failure was no longer unexpected. It was anticipated, studied, and engineered out. These changes added weight and cost. Canopies became thicker. Frames grew more robust. Visibility, once pursued at any price, now competed with survivability. The balance shifted decisively. Pilots accepted slightly reduced fields of view in exchange for confidence that their cockpit would not betray them at altitude. The legacy of those early failures reshaped certification standards worldwide. Regulatory bodies rewrote requirements for transparent structures. Fatigue life analysis became mandatory. Damage tolerance replaced strength as the primary metric. Designs were no longer approved based on whether they could withstand a single extreme event, but on whether they could survive thousands of ordinary ones. Modern cockpits reflect this philosophy. Their canopies are marvels of layered engineering, their shapes informed by fracture mechanics rather than aesthetics alone. The clarity pilots enjoy today is engineered clarity, protected clarity, clarity designed to endure. The invisible degradation that once haunted early aircraft is now a central concern. Sensors monitor structural health. Inspections target known fatigue hotspots. Materials are tracked across their service life. The cockpit is no longer ignored. It is respected. Yet the lesson remains unforgiving. Aviation progress is often driven by ambition. Ambition pushes materials beyond comfort, sometimes beyond understanding. The failures of early cockpit visibility were not accidents. They were consequences. Consequences of believing that what looks strong must be strong, and that what has not failed yet never will. In aviation, failure does not announce itself loudly. It whispers through microcracks, through distorted light, through subtle changes dismissed as irrelevant. Those who listen early survive. Those who do not leave lessons behind, embedded in standards, procedures, and thicker canopies. The Vault records those lessons. The industry's response to cockpit failures did not unfold overnight. Even after forensic evidence became undeniable, resistance persisted. Redesign meant admitting that decades of accepted practice were flawed. It meant grounding aircraft that symbolized national pride, technological dominance, and enormous financial investment. Yet physics offered no compromise. The degradation continued whether acknowledged or not. As redesigned canopies entered service, older aircraft remained in operation under increased scrutiny. Engineers introduced inspection intervals never before applied to transparent structures. Specialized lighting revealed stress whitening near canopy edges. Polarized filters exposed birefringence patterns, visual signatures of internal strain. For the first time, technicians could see damage that had always been present but never understood. These inspections revealed a disturbing reality. Many aircraft were flying with canopies already deep into their fatigue life. Cracks existed not as isolated defects, but as networks. Some had been arrested temporarily by local stress redistribution. Others were dormant only because operating conditions had not yet aligned to trigger failure. The margin of safety was thinner than anyone had believed. To understand the risk, engineers modeled crack growth under real operational profiles. Short-haul aircraft accumulated pressurization cycles rapidly. High-altitude interceptors experienced extreme thermal gradients. Training aircraft endured repetitive maneuvers that flexed cockpit structures aggressively. Each mission profile imposed a unique fatigue signature. No single inspection rule could cover them all. The realization forced a shift in mindset. Structural integrity could no longer be evaluated solely by strength or stiffness. Time became a critical variable. The cockpit was no longer considered safe because it had not failed yet. It was considered safe only if its remaining fatigue life was known, monitored, and managed. This transition marked a turning point in aerospace engineering. Damage tolerance theory, once applied primarily to wings and fuselage skins, was extended to transparent structures. Engineers accepted that cracks would form. The goal was no longer to prevent cracks entirely, but to ensure they could never grow to critical size before detection. To achieve this, redundancy was introduced at the material level. Laminated canopies ensured that even if one layer fractured, others would maintain pressure integrity. Crack arrest layers redistributed stress away from fracture tips. Fail-safe behavior replaced brittle confidence. The canopy became forgiving, not fragile. At the same time, human factors re-entered the discussion. Early cockpit designs had promised unmatched visibility, but failures revealed a deeper truth. Clarity without reliability was an illusion. A pilot distracted by distorted vision or sudden glare was already compromised. The new generation of cockpits aimed for visual stability across the aircraft's entire service life, not just on its first flight. This required unprecedented collaboration between material scientists, structural engineers, and optical specialists. Transparency was treated as a performance parameter equal to strength. Light transmission, refraction stability, and aging behavior were measured, modeled, and controlled. The cockpit evolved into a multidisciplinary system. Meanwhile, regulatory frameworks struggled to keep pace. Certification authorities rewrote standards, often reactively, in response to discovered weaknesses. Requirements for full-scale fatigue testing of cockpit sections became mandatory. Accelerated aging tests simulated ultraviolet exposure, humidity, and temperature cycling. What had once been optional became non-negotiable. Aircraft manufacturers absorbed the cost reluctantly, but the data was irrefutable. Designs that survived extended testing proved dramatically more durable in service. Incident rates declined. Confidence, this time grounded in evidence, slowly returned. Yet the scars of earlier failures lingered. Accident investigations cited cockpit visibility issues as contributing factors long after structural fixes were implemented. In some cases, pilots misjudged horizons due to optical distortion in aging canopies. In others, sudden canopy failures during high-speed flight left no chance for recovery. Each event reinforced the same lesson. The cockpit is not a window. It is a critical structural organ. As aviation entered the digital age, monitoring technologies added a final layer of protection. Strain gauges embedded near canopy frames measured real-time loads. Acoustic emission sensors listened for the ultrasonic signatures of crack growth. Data streamed continuously, transforming the cockpit from a passive structure into an active diagnostic component. This capability fundamentally changed maintenance philosophy. Instead of waiting for scheduled inspections, engineers could track degradation as it occurred. Aircraft were removed from service based on condition, not calendar time. Fatigue life became a managed resource, not a guess. Looking back, the early obsession with visibility appears both understandable and naive. Pilots demanded better sightlines. Designers delivered them with the tools they had. What they lacked was long-term data, computational power, and humility before material science. The failures that followed were not the result of incompetence, but of optimism untempered by experience. That optimism shaped aviation history for better and worse. It drove innovation forward, but it also exposed the limits of assumption-based engineering. The cockpit failures forced the industry to confront a universal truth. Any structure repeatedly loaded will eventually fail unless designed with fatigue in mind. Today's aircraft carry that knowledge forward. Every transparent surface is engineered as carefully as a wing spar. Every interface is treated as a potential fracture origin. Every design decision acknowledges time as an adversary. The sky did not change. Physics did not change. Only understanding did. And that understanding was paid for in grounded fleets, shattered canopies, and moments where confidence met reality at cruising altitude. The lessons endure, embedded in standards, software, and layered transparency that no longer lies about its strength. The vault preserves those lessons, not as warnings, but as evidence of how aviation learns, slowly, expensively, and irrevocably. Despite new standards and reinforced designs, the legacy aircraft still flying represented a fragile bridge between two eras of engineering thought. They carried modern pilots inside structures conceived under obsolete assumptions. Every flight was a negotiation between accumulated fatigue and operational necessity. Engineers knew this. Operators knew this. And yet, the aircraft continued to fly because aviation rarely has the luxury of stopping completely. The fourth phase of the story unfolded when multiple variables aligned at once. High-altitude cruise, maximum pressurization differential, a canopy already weakened by decades of cyclic loading. The physics of failure did not require negligence or extreme maneuvering. It required only time. At altitude, the cockpit is a pressure vessel embedded in a larger one. Internal cabin pressure pushes outward uniformly, but the canopy responds differently from metal skin. Transparent materials deform more, flexing under load. Frames resist that movement, creating localized bending moments. These moments concentrate tensile stress along edges and fastener lines. As long as cracks remain below critical length, the structure survives. When they do not, survival ends abruptly. In the moments before failure, there is no audible warning, no vibration spike, no cockpit indication. The crack grows silently until the stress intensity factor exceeds material toughness. At that instant, fracture becomes unstable. The crack accelerates faster than sound can travel through the material. The canopy does not leak. It disintegrates. Rapid decompression is not a gradual equalization. It is a shock event. Air expands outward violently, generating transient loads that far exceed static design values. Loose objects become projectiles. Structural elements experience sudden load reversals. The pilot is subjected to extreme aerodynamic forces that pin limbs backward and collapse lungs in milliseconds. The cockpit, once a controlled environment, becomes an open conduit to the stratosphere. Wind noise overwhelms all sound. Vision is reduced to chaos as debris and ice crystals fill the space. If the aircraft remains intact long enough, hypoxia sets in almost immediately. Consciousness fades in seconds. From an engineering perspective, the sequence is brutally efficient. Structural failure propagates. Systems fail not because they are defective, but because their environment ceases to exist. Controls lose effectiveness as airflow patterns collapse. The aircraft enters uncontrolled attitudes. Recovery, if possible at all, depends entirely on altitude, redundancy, and chance. In incidents where the aircraft survives initial failure, post-flight inspection reveals a forensic map of destruction. Fracture edges show classic brittle failure patterns in transparent layers, transitioning to ductile tearing in metal frames. Fasteners are bent or sheared. Sealants are pulverized. The canopy frame itself may deform plastically, evidence of loads far beyond design intent. Investigators reconstruct these events frame by frame. Pressure sensors, flight data recorders, and wreckage geometry provide the timeline. Failure initiation points align precisely with known fatigue hotspots. No mystery remains. The catastrophe was inevitable once the crack reached critical length. The immediate aftermath ripples outward. Fleets are grounded again. Operators reevaluate risk tolerance. Aircraft nearing the end of their service life are retired prematurely. Others undergo costly retrofits. Confidence erodes, not just in specific models, but in the assumptions that kept them flying. This phase marks the collapse of denial. The industry no longer debates whether cockpit visibility designs were flawed. The question becomes how such flaws were tolerated for so long. The answer lies in the culture of incremental trust. Each safe flight reinforces belief. Each uneventful landing delays reckoning, until the system runs out of margin. Engineering reviews conducted during this period are unforgiving. Design decisions once justified by weight savings are re-examined under fatigue life calculations. Trade-offs made decades earlier are quantified in terms of crack growth rates and failure probabilities. The numbers are stark. It becomes clear that early cockpit designs operated dangerously close to their endurance limits from the beginning. The margin was consumed not by abuse, but by normal operation. Every flight paid down a debt that no one tracked. When the account reached zero, physics closed the balance. This realization reshapes how engineers think about catastrophic sequences. Failure is no longer viewed as a sudden anomaly. It is understood as the final visible moment of a process that began years earlier. The canopy did not fail on that flight. It failed incrementally on every flight before it. As a result, the definition of safety evolves. It is no longer enough that a structure can withstand a given load once. It must withstand it repeatedly, predictably, and with detectable degradation. Safety becomes probabilistic, not absolute. Modern analysis tools allow engineers to simulate entire service lives before a prototype ever flies. Crack initiation sites are predicted. Growth rates are calculated. Inspection intervals are defined mathematically, not heuristically. The cockpit is modeled as a living structure, aging from its first pressurization. Yet these tools exist because earlier aircraft failed without them. The catastrophic sequences of canopy failure forced aviation to confront its blind spots. They exposed the danger of prioritizing performance metrics without understanding their long-term cost. In retrospect, the drama of these failures is not in their violence, but in their predictability. Every fracture surface tells the same story. Every investigation reaches the same conclusion. The tragedy lies in how long it took to listen. The cockpit, once designed to give pilots mastery over the sky, revealed a deeper truth. Mastery is conditional. It depends on respect for materials, for time, and for the invisible processes that govern both. When the canopy fails, it does not betray the pilot. It obeys physics. The betrayal, if it exists, occurred much earlier, at the moment when confidence replaced caution. Aviation's progress is measured not only by what it builds, but by what it learns to fear. The catastrophic sequence of cockpit visibility failures etched a permanent warning into engineering culture. What you cannot see can still destroy you. The vault records this phase without spectacle because the spectacle is unnecessary. The violence of decompression speaks for itself. What matters is the lesson carried forward, written into every reinforced frame and every layered canopy that followed. The impact of cockpit canopy failures extended far beyond the aircraft in which they occurred. Once the immediate emergency ended, whether in a crash site scattered across terrain or an aircraft limping back to a runway with its cockpit torn open, the consequences began to propagate through the entire aviation system. The failure was no longer isolated. It had become systemic. In the hours following a confirmed canopy failure, operators initiated emergency procedures that had rarely been rehearsed at scale. Aircraft of the same type were grounded preemptively. Flight schedules collapsed. Training pipelines halted. Missions were canceled not because of engine faults or structural wing issues, but because a component once considered peripheral had proven capable of destroying the entire machine. Hangars filled rapidly with aircraft awaiting inspection. From the outside, they appeared intact, paint unmarred, airframes clean, yet each cockpit was now suspect. Engineers approached them cautiously, aware that what mattered could not be seen without tools and time. The fleet was grounded not because of visible damage, but because of uncertainty. Maintenance crews began methodical disassembly. Canopies were removed, tagged, and cataloged. Frames were stripped of sealant. Fasteners were extracted one by one. Each component entered a chain of custody more commonly associated with criminal investigation than routine maintenance. Serial numbers were logged. Service hours recorded. Pressurization cycles counted. The magnitude of the problem revealed itself quickly. Aircraft with no recorded incidents showed advanced fatigue damage identical to those that had failed catastrophically. Crack initiation sites were found in predictable locations, but their growth stages varied widely. Some canopies were weeks from failure. Others had likely crossed the threshold already, surviving only because conditions had not yet aligned. This realization triggered an operational crisis. Risk could no longer be managed incrementally. Either the fleet was safe, or it was not. And without immediate modification, no one could guarantee safety. The cost of inaction was unacceptable. Regulatory authorities responded with grounding directives that bypassed normal review timelines. Airworthiness certificates were suspended pending inspection and modification. Manufacturers issued service bulletins that rapidly escalated into mandatory compliance orders. The language shifted from recommendation to requirement. For operators, the financial impact was immediate and severe. Grounded aircraft meant lost revenue, disrupted logistics, and contractual penalties. For military fleets, readiness dropped overnight. Training sorties were canceled. Operational coverage gaps appeared. Commanders faced the uncomfortable reality that their most advanced aircraft could be rendered ineffective by a transparent panel. Public confidence followed a similar trajectory. Media reports focused on the drama of decompression and shattered cockpits. Technical nuance was lost, but the message was clear. Something fundamental had been missed. Passengers questioned aircraft safety. Pilots questioned their protection. The cockpit, the place of human trust, had failed visibly. Internally, manufacturers faced a reckoning. Engineering teams were assembled under intense pressure. Past design reviews were reopened. Decisions made decades earlier were scrutinized with modern understanding. Why were certain geometries approved? Why were fatigue tests limited? Why were transparent structures exempt from the same rigor as metal skins? Answers were uncomfortable. Some decisions were driven by competitive pressure, others by incomplete data, many by optimism. In some cases, engineers had raised concerns that were deprioritized in favor of performance targets. The aftermath forced those voices back into the conversation. The crisis phase transformed investigation into action. Temporary fixes were rejected. Operators demanded permanent solutions. Retrofit programs were launched at unprecedented speed. Canopies were redesigned, manufactured, and installed across entire fleets. Structural reinforcements were added to frames. Inspection intervals were tightened dramatically. Aircraft returned to service gradually, each one carrying documentation thicker than the canopy it replaced. But even as operations resumed, the psychological impact lingered. Pilots who had experienced canopy failures described lasting effects: distrust of the cockpit environment, heightened awareness of sounds and sensations previously ignored. The failure had not just damaged aircraft. It had altered perception. From a systemic perspective, the immediate aftermath reshaped safety culture. Transparency was no longer synonymous with simplicity. It was recognized as complexity disguised by clarity. Training programs began emphasizing structural awareness of cockpit components. Maintenance manuals expanded sections dedicated to transparent materials. The cockpit was elevated from accessory to critical structure. Data collected during the grounding period proved invaluable. Engineers compiled fatigue damage statistics across fleets with unprecedented resolution. Patterns emerged. Aircraft operating in certain climates showed accelerated degradation. High UV environments weakened polymers faster. Cold soak cycles intensified thermal mismatch. Mission profiles mattered more than age alone. This data informed future design and maintenance philosophy. Usage-based life limits replaced calendar-based assumptions. Aircraft were no longer treated as identical units aging uniformly. Each cockpit accumulated its own structural history. Safety became individualized. The immediate aftermath also triggered a broader industry conversation about hidden vulnerabilities. If something as visible as a cockpit canopy could fail invisibly, what else was being overlooked? Engineers revisited other components traditionally considered low risk. Fairings, radomes, sensor windows. Transparency was reclassified from benign to potentially critical. In parallel, certification authorities acknowledged their role. Standards that had evolved slowly were now accelerated. Committees convened to revise fatigue requirements for non-metallic structures. Certification pathways were tightened. Demonstrations of durability became mandatory, not discretionary. The crisis period ended not with closure, but with normalization. Aircraft returned to service under new rules, new inspections, new designs. Flights resumed. Confidence stabilized, though it never fully returned to its former innocence. Aviation had learned, once again, that safety margins erode quietly. The immediate aftermath of cockpit visibility failures left a permanent imprint. It proved that failure does not require exotic conditions. It requires only time, repetition, and an assumption left unchallenged. The fleets that survived did so because the industry chose to stop, look inward, and accept what physics had been signaling all along. The cockpit, once treated as a window, emerged from the crisis as a lesson. A lesson written not in theory, but in grounded aircraft, emergency directives, and redesigned transparency. The aftermath did not end the story. It forced aviation to continue it differently. The Vault preserves this moment not as a turning point of drama, but as a turning point of discipline. Because in aviation, the aftermath is where learning either happens or is postponed until the next failure.